Okay, so we already discussed regarding on thermal equilibrium. It is when an object, two object, will reach a final equivalent temperature. Okay, so that is the key point when it reaches thermal equilibrium. All of the system or things within the system that is contact with each other will eventually acquire one only temperature. The final temperature will be the same. So that is the concept. Okay, so what happened here? So what we already discussed before is that the amount of heat transfer from one body, which is can be given by Q equal to MC del T, Q equal to MC del T. So this is the equation that describe the heat flow. It's not describe the amount of heat within an object, but there is a amount of heat being transferred from one object and the other. Okay, so by mean of transfer, if I were to have a system, okay, so this is the red box is a system, and then within the system there I have to another block. So this green block is within the red system. So if one receive, let's say if A receive, then A have to receive from somewhere, which is obviously B. Okay, so let's say if B if A been if A lost, then it must receive by somewhere, something else within the system, which is obviously B. So if I were to have more than that, okay, more than that, then it can be that A here transfer to both B and C, but it is not important how much it might be received, a little bit from B and then A as well, but that does not important, because we can just count the amount of make an equivalent, how much heat transfer here, and then how much heat transfer here, and then how much receive into one whole equation. So that equation been guided into the concept of thermal equilibrium, where the temperature is the same. So because of this equation is so profound in such a way that it will provide us whether the on object will absorb in temperature, or to lose to absorb energy, or to lose energy, to gain heat, or lost heat, by simply having the temperature decrease. Means that, let's say, from 10 degrees Celsius to 20 degrees Celsius. So this is final, this is initial. And if we do the maths for this change in temperature, because the mass and the specific capacity will always going to be positive, whereas the change in temperature here is always depend on the final minus initial. So in this case, our final will be 20 minus 10. Then you will see that this object will receive energy. Okay, it will gain energy. Okay, whereas if we have a condition when an object is initially at 60 degrees Celsius, 60 degrees Celsius, and goes to 25 degrees Celsius, then if you do the equation as well, Q equal to MC del T, then we will see that the change in temperature, so this is final, this is initial, we will see that 25 minus 60 will give you a negative 35 degrees Celsius. Okay, so it means that this object will lose heat energy. Okay, so having this within the equation, we just need to whenever we want to determine need to solve problem where it at thermal equilibrium, it is where the summation of all of the heat transfer should be equivalent to 0. Okay, so in a way that if we have dealing with this object A, B, C, then the only way, the easiest way to solve this is the amount of heat transfer from A plus the amount of heat transfer from B plus the amount of heat transfer from C should be equivalent to 0, because there shouldn't be a net of flow going out of the system. Okay, so if we don't have this one equal to 0, it means that sum of energy is being, if it positive, then you're going to receive amount of energy from the outside. If it negative, then you're going to lose certain amount of energy from the to the outside of the system. So whereas in some of the example, I will show you that it will not, the energy will just circulating within the object, within the system. It does not go outside. So then the easiest way is to do this, and then let the, whether it's absorbed or dissipate or lose the energy, it will be determined by itself through the temperature difference. Okay, so let's go to one example. Okay, like this. So that, just now is all of them are being just elaborated. So here you can this is what we call, we can consider this one as calorimeter, but I think we can go to the problem, example problem, see what does it mean. Okay, let's try okay, this one have a calorimeter. Okay, so 75 gram of calorimeter contain of 500 gram of water at 24 degrees. So if you look at here, you see it have calorimeter, and then it contain water 500 gram. So this is water, it's 500 gram, and then it said that at temperature, so it combine calorimeter and water at 24 degrees Celsius. It means that this calorimeter, the container there, and the water, both of them at 24 degrees Celsius, means that both of them already reached thermal equilibrium, means that there will be no heat transfer, no net heat transfer. Okay, proceed. If 55 gram of aluminum or at 70 degrees Celsius is dropped into a calorimeter, and find the temperature of the system, the final temperature of the system. Okay, so it means that we have another object which is aluminium at 70 degrees Celsius. So it's been dropped into a water which is at the temperature of 24 degrees Celsius. So this is where we happen is that we have a closed system where within the system there we only have aluminium, water, and also a calorimeter. So the transfer of heat is always going to be in between this. You cannot have other beside outside here. So it means that if I were to have Q of aluminium, so whether it's received or lost, it doesn't matter. The equation will, the change in temperature will decide that, and plus Q water and plus Q calorimeter. This is for apply for equilibrium. This is apply for when it leaves to form equilibrium in temperature. So this should be equal to 0. Okay, so having this, we just need to add all the values. So we need to track down QA, aluminium is 55 gram, which is 55. So remember to make sure leave everything in kilogram, because this so see the unit there, when we use the aluminium here, make sure that we use SI unit, because this one kilogram. Okay, if the given value is gram, then maybe you can use a gram as well for aluminium, but here given by kilogram, unless you want to change this one into gram. Okay, I think it's not wise to do so. Okay, so here 900, and the change of temperature. So remember the change of temperature, Q to M C del T. So the change of temperature, how you write this, you want to determine the final temperature. So what happened when we leave everything to thermal equilibrium? Eventually at thermal equilibrium, all of this will have only one temperature, which is what we call temperature final. So we can just replace this one temperature, because the change of T here is always final minus initial. So this is final minus initial. So what is the initial? It is 70 degrees Celsius. Okay, so just leave it 70 lah. Okay, so then the next one, do the same thing. For water, we have 0.5 kilogram. The specific capacity for water, so check this one in kilogram. Okay, 4186. So you need to be careful as well. Make sure that the unit here is consistent, joule, because we don't want to have add up 10 joule plus 10 kilojoule become 20 joule. This is wrong. Okay, it should be 10,000 and 10 joule, because this is of kilo here. Okay, so that one also you need to be careful. We don't want this thing to happen. Okay, so again, let's find the change in temperature for water. So again, the final temperature will be TF. So we just need to look the initial temperature. Initial temperature is 24. So this one, because it's change of temperature, you remember that the Kelvin and the Celsius, the difference between the scale are the same. Means that 0 to 100 is 100. 273.15 to 373.15 also 100 in different. So then if I were to change the Fahrenheit, the Celsius into Kelvin, the difference in temperature also going to be the same. Okay, so then in this case it doesn't matter if you even if you use Celsius. Okay, so then next one is calorimeter. Okay, calorimeter. Calorimeter, where is it? Okay, so the calorimeter weight is 75 gram, so it should be 0.075, and then we need to have the specific heat capacity, which is 38. Yes, the calorimeter is in copper. Calorimeter in copper, but if you don't quite sure, you can always ask. So calorimeter is copper, 387. 387. So the temperature is different also. TF minus 24, the same temperature. This one should be equivalent to 0. So solve this by having all of this, because you eventually this. So this is just mathematics, but I'm going to show you the easy technique. Okay, then eventually this one will multiply by both of this, right? So you can just leave the side of TF to the left side, and then the one that multiply with the right side to the right side of the equation. So then we're not going to have any zero anymore. So it's going to be something like this, 0.05. So just going to leave it not multiply just yet, or you can do the solve the multiplication right away also can, whichever that you might think is useful for you. So 0.5, just write it down back, 6, so TF as well, plus 0.075, 387 TF, and then the other side is going to be technically similar. So 900, but this one we're going to do take the other part because we already moved to the right. So 900, so this multiply by 70. Do the same thing for the other two as well. 86, 24, and then plus 0.075, 387 multiplied by 24. Okay, so obviously you see, we remember that we still want to find TF, so you factorize the TF, and then everything that left inside the column, put it on the bottom of this, then solve that. You should get the answer there. Okay,